Alright, Assalamualaikum warahmatullahi wabarakatuh. So now let us move to topic number 2, okay, with the title of Balanced Three-Phase System. So some of the contents outlined. So number 1, introduction, three-phase system. So three-phase source connection, right, voltage and currents in the three-phase circuit. So delta Y transformation, three-phase load connections. Alright. So learning outcomes after completing this chapter, you will be able to explain the various source and load configuration and the advantages and disadvantages of each, okay, for the various source and load configuration. So secondly, alright, phasor equation for voltage and current in star and delta connected sources. Okay, so how to actually write the phasor equation in terms of voltage and current. Okay. Number 3, draw phasor diagram. Okay, for voltage, again for voltage as well as current in star and delta configuration. And then finally, analyze the balance three-phase circuit in both, again, star and delta connection. All right. 2.1 introduction. So review three-phase generation. Okay, so this is what we have seen earlier in topic number 1. So we have our generator, for example. So we have phase A. So we have another phase A which is connected together all the way to neutral point. And then we have the second phase which is B, and this is interconnected. Okay, B and B interconnected and all the way to neutral point. So similarly for the third phase in green over here, C, it is the winding, these two coils are integrated, okay, and all the way to neutral. So the output, if we can measure, okay, in terms of sinusoidal waveform, so this is again for A, alright, so phase A, so this is phase B, the second phase, as well as phase C. Okay, so due to this direct, clockwise rotation. Okay, so S stands for south and N stands for north. Okay, so we have again the diagram, okay, the three-phase diagram connected in star. Okay, so we have VBN, VIN, VRN, and then between line to line, so for B, R, and Y line. Okay, so phase voltage, again, so we have VRN, everything connected to N in this particular configuration, star. So it is known as phase voltage. So line voltage between B and R, okay, B and R and Y, as well as B to Y. Okay. So phase line current again, so since this is a star configuration, so we simply have phase line equal to phase current equal to phase line current. So this is three-phase load. Okay, distribution system. So what happened in this particular system? So this topic, we will analyze three-phase circuit found in the low voltage distribution system around 11 kV or 33 kV, so which is the final stage in the delivery of electric power. So again, we start with the generation side over here, the power plant. So we have the Y to Y connected of transformer, okay, for example, so a step up transformer, and then this transmission line, right? So we have 400 kV or 235 kV long distance over here, okay, before it comes to terminal station where we have transformer with on load tap charger. This is the type of transformer in order to step down the voltage to 132 kV or 66 kV, the sub-transmission region. Okay, and then another substation transformer, zone substation transformer in details before we come to distribution side. Okay, so from distribution side, so this is the bus bar, okay, in the substation. So we have the distribution transformer again along this one. Okay, this is another distribution line. So we take this transformer, okay, so the distribution transformer, okay, to step down from 11 kV, for example, down to three phase and single phase supply. So 415 is your three phase supply, and 240 is your single phase supply. So this is known as low voltage distribution system. So one single phase may go to your house, right? So residential area. So three phase may go to industrial zone, for example, factory, for example. Right? So it may go to big building, may go to hospital, etc., etc. Okay. And then polyphase systems where all lines voltage and current are equal to each other. So this is how we define balanced polyphase system. So we can simply assume that line voltage and current so are equal to each other. So just to recap what we have seen earlier, so electricity system in Malaysia, what have been defined by the TNB, so voltage transmission network, either these three value, all right. So distribution system or voltage may fall under this value, three value, okay. And then however, some part of Peninsula Malaysia, especially Johor and Perak, so distribution voltage may include 22 as well as 6.6 kV. So frequency, supply frequency, ethical frequency is about 50 Hz. Okay, so this is what I have been highlighted earlier. So Malaysia power network feeding the low voltage distribution system is the distribution network, again 11 kV lines or feeder downstream of 33 kV substation. Okay, where each 11 kV feeder emanates from 33 kV substation branches further into several subsidiary 11 kV feeders to carry power close to the load point. So example of load point is localities, the industrial zone areas, villages, housing area, etc., etc. Okay. So at these load points, so what happened at these load points? So transformer further reduce the voltage from 11 kV. This is what I have discussed in the previous slide. So down to 400 volt, for example, to provide last mile connection through 400 volt feeder, also called as LT or low tension feeders, to individual customer, either at 230 or 240. It comes with the tolerance plus minus 10%, for example, as a single phase supply, or at 400 volt as three phase supply. Again, it comes with the tolerance 10%, so or 5%, for example. So the value or the final voltage may vary from 400 up to 400 or 390, all right, 380 or up to 440, for example. It may vary, something like here. So normally we have 240, so it may vary from 220, okay, up to maybe 240, 45, for example. All right. So what is there in a substation? Okay, typically down from 111 kV down to 415 kV. Is it kV? No, it's not kV. So let me erase this one. Okay, so let me erase or let me remove this one. So 11 kV from the distribution system down to 415 voltage or volt at substation. So incoming 11 kV from the feeder. So VCB, so this is vacuum circuit breaker. So for protection, safety purpose, so why VCB? Because to comply with the high voltage or low tension over here, 11 kV. So we have the the current transformer. So for metering purpose and again for protection, yes, 11 kV at the primary side of the transformer TX. This is a symbol for transformer. So it has the value of the level of voltage 11 kV has been stepped down to 415 volt at the primary output of transformer over here. So this is the output, or this is the secondary part. This is the input or the primary part of transformer. So ACB is the most appropriate type of circuit breaker to handle or to deal with 415 volt. So again, for protection, ACB over here, a circuit breaker for protection, and then here comes the CT current transformer for metering, okay, to show the value of 415, for example, or the current carried by the line, and as well as the protection. Okay, so again, this is the bus bar for the 415 volt after being stepped down and again being distributed into several lines with its respective MCCB, stands for molded case circuit breaker, another type of protection. And circuit breaker, current transformer, for each individual lines before it comes to consumer, for example, the hotel department, library, school building, hospital, etc., etc. Right. Okay, a bit on the circuit breaker. So we have seen the vacuum circuit breaker where we locate or we put inside the 11 kV substation, for example, and this is a circuit breaker to deal or to carry 415 volt. Okay, so it depends on the structure or the design of the circuit breaker to hold or to withstand 11 kV. So this is designed for, this is designed for 11 kV. So ACB designed for 415V volt. So A circuit breaker are usually used in low voltage application below 450 volts. Okay. Meanwhile, vacuum circuit breaker or CV indoor is for 11 kV. Okay. So feeder, so this is the line, the cable over here, so-called feeder, could be either an overhead line or underground line. So what we see here is actually underground cable. So in urban areas, so where the population is high, the density of population is high, so many people over there, so the length of N 11 kV is generally up to 3 kilometers because they live in very short distance area. Okay, and the density is a very compact population. The density of population is very high, so people live not very far, very close from one to another, meaning so 3 km feeder is sufficient for this type of area. So on the other hand, so in rural areas, the feeder length is much larger, up to 20 kilometers, because at rural area, village area, kampung area, for example, the suburban area, so people stay quite far from one family or one house to another. So the density of the population over there is very low. So meaning feeder, okay, the cable length over here may up to 20 kilometers. So, and then 415 feeder should normally be restricted to about 0.5 to 1 kilometer. Unduly long feeders lead to low voltage at the consumer end. So due to some losses in terms of heat, etc., etc., harmonics, and etc., etc. Okay, so it is advisable to have 415 feeder, okay, at this short distance. Substation transformer usually use the grounded Y to grounded Y configuration. So Y to grounded Y, okay, configuration. So however, substation transformer are multi-winding transformer that also have a tertiary delta winding over here. Okay, so this is the design for the diagram for the multi-winding transformer. So this delta winding, the tertiary, the third one. So we have the third winding over here. All right. So the tertiary one is actually to prevent harmonics from circulating in the electrical transmission system. So to avoid harmonics where the harmonics may become a load or to increase the load of the system, okay, and then causing the efficiency of the transmission line become worse or less, that cause the instability of the transmission. And this also to stabilize the neutral point when loads become unbalanced. So this one. So we meaning the third one is very helpful. Okay, when we come to harmonics issue and stability of the neutral point whenever loads become unbalanced. When loads become unbalanced, perhaps failure in one of the line, for example, this transmission line, it is fall into ground and being grounded. So this means the three system over here, the first system, the second system is still operating at normal rating of voltage, for example, but this one has been grounded because the cable fall or disconnected and fall onto ground, being grounded. So this means this is a zero voltage, and the system of line 1 and line 2 become unbalanced. All right. So loads become unbalanced, for example. So circuit configuration. The circuit configuration used by the distribution system to supply three-phase power to industrial and residential consumers depends to some extent on the type and size of load to be connected. So it depends on the consumer. So it is either industrial, which consume three-phase 415, or residential consumer consume 250 volt, which is a single phase. So several methods to connection are possible. So we do have for three-phase, three-wire. So combination between Y and Y, wire delta and delta Y. For three-phase, four-wire, only applicable to Y and Y, because of course we have neutral to neutral, for example. So three-phase system may or may not have a neutral wire. So what is neutral wire? So it allows the three-phase system to use a higher voltage while still supporting lower voltage single phase appliances. So we have seen, for example, all right. So we have seen, for example, here, okay, the N. So we have R. So we have VRN is the phase voltage which is supporting lower voltage or single phase appliance. So this is single phase. Okay, but with the same system, the same configuration. So we do have the line-to-line voltage, which is VRY, and we may upgrade from VRN, the single phase, to three phase. Okay. So in high voltage distribution station, it is common not to have a neutral wire. However, so in high voltage distribution stations, common not to have a neutral wire, as the load can simply be connected between phases, phase-to-phase connection. So since the load itself can be connected between phases already and neutral point over there, so it is common not to have neutral wire in the high voltage distribution. Okay, three-phase, three-wire system. This is no non-neutral. Okay, obviously neutral because we have delta, all right, delta configuration. So three-phase line, line number one, R to R. So we have the second one is Y to Y. We have the third one is B to B, from source to load, all right, R, Y, and B. And then what about three-phase four-wire system? Yes, for example, Y to Y, we do have the neutral connection. So the port one is actually neutral conductor. This N, okay, is connected to this N. Okay, R, Y, B remain the same. And then the port wire is actually referring to neutral conductor. Then balance three-phase system. So the line and phase current and voltage, line and voltage in all phases are equal in magnitude and separated by 120 degree each, and impedance in all three phases are identical. Okay, the impedance. Okay, so we have Z, for example, Z in R phase equal to Z in Y phase, and this is equal to Z in B phase. Okay. Okay, this is for example for the load, and then this is for an example for the source. Okay, the voltage source. So this is load. Okay, V and R. So they are all identical. They are all equal between one phase to another. R, B, and Y. Here also same goes here. So this one and this one. Okay, so Rn, Vbn, Vyn, 120 degree separated each. Alright, separated each. So remember, this is positive sequence because we have R, Y, and B. Okay, so from R to Y, from Y to B, so RYB is referring, this is for just for revision. Remember just now, just a few slides earlier in topic 1. So this is positive sequence. Okay, an unbalanced system is one in which any of the foregoing requirements are not met. Okay, so we will come to the unbalanced system in later topic. Okay, so solving problem in balanced system is simple. It's much simple because there are symmetry, which allows us to make a per phase analysis. That means instead of three phase, now we go down to single phase and analyze it, and this is actually equal to three phase. All right.